Welcome to lecture series on Wakedale Verilog under EPG Pathshala. In this module, you will learn about VLSI design process. Almost all electronics gadgets or electronic products, they use integrated circuits. Integrated circuits are normally used to reduce the cost, power and the design complexity in the design. We know that all the ICs are classified under four major categories: small scale integrated circuits SSI, medium scale integrated circuit MSI, large scale integration, that is LSI, and very large scale integrated circuits, that is VLSI. VLSI circuits include more than 10,000 to 1,000,000 transistors per chip. According to Moore's law, the number of transistors or devices per chip are doubling every 18 to 24 months. Now, we have seen the trend that the number of transistors or the devices per chip are doubling even in the short span, not 18 to 24 months. Now, in order to understand this complete design process, we will begin with the conventional design process of the circuits, and then we will switch over to the digital IC system design using VLSI. In VLSI design process, there are 6 major steps. One can start with the design process, synthesis, simulation, then working on the physical design, testing and verification. Whenever some person is designing the integrated circuit, naturally he has to think about the design complexity. That is why the designing is based on the methodology suggested by Gajarski chart, or popularly known as Y chart. In this, the design is carried out at 3 different domain levels, and these 3 domain levels could be structural, physical or behavioral domain, and we may consider multiple models for the design, and there are different levels of design. In this module, we will learn about the implementation process as well. Let us begin with the journey of VLSI design. Let us now get familiar with learning objectives of the module. Before discussing the VLSI design, it is necessary to study the conventional design process. To study different stages of development of VLSI IC, initially Y diagram for VLSI design is explored. Next step is to design and learn about the different abstraction levels in the Y diagram. For any digital system designer, it is important to know the digital system design / development task. Digital systems represent information using a binary system, where data can assume one of only 2 possible values and processing using digital logic. Digital systems were initially designed using available SSI and MSI ICs. Nowadays, whenever there is a need to design a digital system for a given digital function, designer utilizes his knowledge and skills to select a standard set of ICs along with minimum interconnections between them. The simplest approach to design digital systems is a mixture of top down and bottom up approaches as shown below. Let us now discuss a simple design approach. Step 1. Decide the requirements at the system level and further translate them to the circuit requirements. Step 2. Identify the major functional blocks required, like timer, DMA unit, register file, etc., like the one in the design of a processor. Step 3. Whenever a function can be realized using standard IC, use the same, for example, counter, multiplexer, flip-flop, gates, etc. Step 4. Whenever the above stated things is not possible, form the circuit to carry out the block functions using standard ICs. Step 5. Use additional components like diode, transistor, resistor, capacitor, etc. whenever essential. In the conventional design approach, as usual, let us start with a problem definition clearly. System requirements are gathered in terms of input, output and process parameter. With the given digital system requirements in terms of functions, timings and logic, it is possible to design the system using Boolean algebra or K-map. At this stage, it is essential to select necessary components. The physical locations of the components are tentatively planned and then interconnections are made on paper. This generates the physical layout along with the circuit connections. The next step after paper design is to prepare a circuit layout. Once the actual circuit layout is prepared, the netlist is generated, based on which the layout and netlist, the pattern is transferred to the printed circuit board. All the selected components are placed at their position and then circuit components are soldered. After finishing the soldering, the circuit on PCB is tested and verified for desired operation. At this stage, the system test is OK or not. During the testing and verification process, it happens that there is some problem in the functional mismatch, timing mismatch or logic problem. If the expected and implemented functions are different, then it generates a functional mismatch. Designer needs to go back to the circuit design, check the functional blocks carefully and try to locate the error in hardware. Once the desired corrections are made, the remaining sequence of steps can be followed. Once all the bugs are removed and desired functionality is tested, then the digital system is successfully implemented. Let us now study some important tips in designing digital systems. First, good tools do not guarantee good design, but they help a lot by taking the pain out of doing things right. Therefore, select good design tools. Digital circuits have analog characteristics. Therefore, it is important to know the analog characteristics of digital system. Know when to worry and when not to worry about analog aspects of digital design. Thus, do not worry too much about analog aspects of digital design. Always document your design to make understandable by yourself and others. Thus, keep good documentation. Associate active levels with signal names and practice bubble to bubble logic design. In short, use De Morgan's equivalent whenever necessary. Understand and use standard functional building blocks for design. Design for minimum cost at the system level, including your engineering efforts as a part of the cost. Thus, do not forget to include your engineering efforts as a part of the cost of the system. State machine design is like programming. Approach it that way. Use programmable logic to simplify designs, reduce cost and accommodate last minute modifications. Avoid asynchronous design. Practice synchronous design until a better methodology comes along. Pinpoint the unavoidable asynchronous interfaces between different subsystems and outside world and provide reliable synchronization. Delays and hazards be appropriately handled. Catching a glitch in time saves 9. The above important tip will help the digital system designer to save time, cost and redesigning efforts. The conventional design approach of digital system is not suitable for complex circuit designs like VLSI design, in which more than 10,000 components are involved in integration. With the availability of CAD and EDA tools, the VLSI design has become the order of the day. Even the manufacturing trend is also shifting towards VLSI design due to following reasons. First, increase in functionality of IC. Increase in size of IC due to increase in number of functions / chip. Increase in speed of operation. Increase in density of gates or transistors. Increase in design tools and their variety. As the density of devices in a chip reaches hundreds of millions of transistors, it is impossible for a human being or even a computer to process this huge amount of data directly. In order to manage complexity of this level, it is recommended to describe a system in several levels of abstraction. An abstraction is a simplified model of the system. It shows only the important features and ignoring associated details. The main purpose of an abstraction is to reduce the amount of data to a manageable level, so that only critical information is presented. A high level of abstraction is focused and contains only the most vital data. On the other hand, low level abstraction is more detailed and takes account of previously ignored information. Even though the low level abstraction model is more accurate and is closer to the real circuit, it is very complex to handle. Therefore, development process starts with high level abstraction and concentrates on most important characteristics. As the system becomes clear, finer details are handled and included at lower level. Further, lower level abstraction is also developed. The designer can handle the circuit complexity with the help of hierarchy and abstraction. Hierarchy indicates that the structure of design has different levels of description, and abstraction hides the lower level details. Abstraction helps the designer to limit the number of parts at each level in the hierarchy. Each part can further be divided into subparts at the lower level of abstraction. The division continues till the basic building blocks like transistor of a circuit is reached. A single hierarchy may not be sufficient to describe the VLSI design process. There are three design domains, namely behavioral domain, structural domain and physical domain, each with its own hierarchy. An abstraction based model is a fundamental to all automated design. The Gajarski-Cohen chart or Y diagram describes the different perspectives in the digital hardware design. It shows the different stages of development of VLSI integrated circuit. According to this model, the development of digital hardware is perceived within three domains. The three domains are shown by the three axes producing the Y chart, namely behavioral model or domain, structural domain, physical or geometrical domain. There are 5 hierarchical levels. Outermost circle gives highest level of hierarchy. The 5 hierarchy levels are shown by the 5 concentric circles. Let us label them from the outer or highest level of hierarchy to innermost circle, namely system level, algorithm level, register transfer level, logic level and circuit level. Let us now talk about structural domain. In this domain, a system is described in terms of subsystems. Here, the different subsystems and their interconnections to each other are listed for each level of abstraction. At highest level of hierarchy, there are CPU, memory and IOs. At next level, there are subsystems, FSM, data path, etc. Further, we have ALU, registers and multiplexers. Logic gates or flip-flops are at next inner levels and transistors are at the lowest level of hierarchy. Next domain is geometrical or physical domain. There is information about size, the shape, the physical placement which is included in this domain. At the outermost level, all ICs must be realized on a chip. These chips are further partitioned into several blocks or chips. Blocks are generated by using macros and floor planning is used for implementation. Further details are generated using module plans and standard cells. At lowest level in this domain, we talk at transistor layout level. Let us now discuss about behavioral domain. This domain describes the functional behavior of a system. In this domain, a part of design is viewed as a black box. The relation between inputs and outputs is given without referring to the implementation of the design using system specifications. A behavioral description is used to generate the algorithm with the help of register transfer instructions. These instructions are correlated to obtain logic expression using Boolean algebra to give details of transfer function. In the Y chart, the 5 concentric circles define hierarchical levels in the design process. The abstraction level increases from the inner to the outer circle. The building blocks in the digital design are most commonly used part at the physical level. These parts are the components used in the structural view. Behavioral and physical representations are the descriptions for the behavioral and physical views. These abstraction levels in the Y chart are described below. First, system level. This level of abstraction is also known as processor level abstraction, which is the highest level of abstraction. Blocks used in the structural domain are CPU, memory, bus and IOs. In physical or geometrical domain, chips, board and physical partitions are defined. At this level, the basic properties of electronic systems are determined. In the behavioral model, the block diagrams are used for making the abstraction of the signals and their time response. The behavioral description is like a program written in a conventional programming language, including computational steps and communication processes. The algorithm level. This level is defined by concurrent algorithms in terms of signals, loops, variables or assignments. In the structural domain, blocks like subsystem, data paths, FSMs are defined, whereas in physical domain the blocks or chips are defined. The data representation at this level is more abstract. The behavioral description at this level utilizes general expressions to specify data transfer and uses an extended finite state machine, that is FSM, to describe the system design using register transfer mechanism. All register transfers use a common clock signal. The clock signal functions as a sampling and synchronizing pulse, putting the data into storage components at particular point, normally at rising or falling edge of the clock signal. The next level of abstraction is the logic level. This level is described in terms of behavior perspective by Boolean equations. In the structural view, this is displayed with logic circuit. Typical building blocks include simple logic gates such as AND, OR, NOT, XOR and 2 to 1 multiplexer, as well as very basic memory elements such as latches and flip-flops. Instead of using continuous values, if the signal's voltage is above or below a threshold, then it can be interpreted as logic 1 or logic 0 respectively. In addition to binary values, the input output behavior is described by Boolean equations. The abstraction converts a continuous system to a discrete time system and helps to discard the complex differential equations. Similarly, propagation delay is used to specify the timing of a gate. In the physical/geometric domain, the logical level is described by standard cells. The physical description at this level is the placement of gates or cells and the routing of the interconnections wires. Normally, the area or size of IC is measured in terms of number of gates, which provides an advantage in measurement, which is independent of underlying device technology. Register transfer level. In this level of abstraction, the basic building blocks are some simple registers and data routing elements like multiplexers. Register transfer describes a design methodology in which the data is transferred between storage registers and other logic units. Communication signals are frequently grouped together and interpreted as either unsigned or signed binary state. The physical layout at this level is known as the floor plan. It helps to find the path between storage components and also helps to determine the clock period. Register transfer level. In this level of abstraction, the basic building blocks are some simple registers and data routing elements like multiplexers. Register transfer describes a design methodology in which the data is transferred between storage registers and other logic units. Communication signals are frequently grouped together and interpreted as either unsigned integer or some binary state. The physical layout at this level is known as floor plan. It helps to find the path between the storage components and also helps to determine the clock period. Circuit level. The lowest level of abstraction at the innermost layer in structural and geometric domains is the transistor level. At this level, the basic building blocks are transistors, resistors, capacitors and so on. Circuit level in behavioral domain is described by mathematics using different equations. These differential equations or logical equations or even some type of current voltage characteristics diagrams are also used. At transistor level, a digital circuit is treated as an analog system in which signals are time varying and can take on any value of continuous range. Further, in physical or geometric domain, the description of the transistor consists of detailed layout of components and their interconnections. It basically defines the masks of various layers and is the final result of the design process. Let us now begin with the understanding of design development task. The behavioral, structural and physical domains along with their hierarchies are represented by the Y chart. Each axis represents the design domain and the level of abstraction decreases from outside to the center. In addition to this, the Y chart is a powerful tool to show different design methodologies as shown in the figure. The major problem in VLSI design is the top down design problem. This is pursued by three domains of behavior, structure and physical layout that goes top down towards the more detailed abstraction levels. The designer can select one of the perspectives and then switch from one view to another. The design process may not follow the specific sequence in Y chart. The path drawn in the Y chart indicates a top down design methodology where different parts with known behavior are divided into smaller blocks with simpler behavior and interconnection structures. This aspect provides a transition from the behavioral to structural domain. Each subpart or subcircuit can further be thought of located on the behavioral axis, which provides next path on structural domain. This process continues further lower level of abstraction. This process continues until a low level of abstraction is reached. During this top down approach, starting from behavioral domain at top level, the process of design reaches till the bottom of structural domain at transistor level is reached. The IC layout is not considered during this top down design approach. Now, the designer can follow bottom up approach in physical domain. As a starting point, the circuit is fully specified at the bottom of structural level and the layout is specified in the bottom to top approach, where transistors are grouped to form cells. Cells are further grouped to form modules. Modules further forms macros to reach the final stage at the floor plans. The next higher level of abstraction is block or chip. The topmost level of design is a chip or board or physical partitioning of the system. The tasks involved in design of VLSI IC can be grouped in different categories: logic design, HDL, simulation, synthesis, physical design, verification and testing. Some of the design tasks are clearly visualized as transitions in the Y chart, either within a single domain or from one domain to another, as shown in the figure. Logic design HDL. As a first step in the design, there is a need to obtain clear specifications of the IC. The designer may begin with initial algorithm to be implemented in the hardware and work purely in the behavioral domain. Some designers use general purpose programming language like C at this level. On the other hand, more and more designers use popular hardware description languages HDL to implement the design. These languages basically provide the description of the hardware. Presently, VHDL and Verilog are the most commonly used languages. In many CAD tools, the hardware entry can be made using schematic editor program. In this program, the design is entered in the form of a blocks consisting of circuits and their interconnections. Simulation. A formal description of hardware can be generated with the help of HDL. HDL description becomes more effective when a simulator is available with it. Simulation helps the designer to detect errors in the HDL code. Simulator basically helps the designer to verify the circuit. In many CAD tools, the simulator can handle hardware description as well as the software to cope with the hardware-software co-design approach. At this level, it is possible to carry out fault simulations as well. It checks the faults or imperfections in fabrications using a set of test vectors or test patterns. This task can be automated with the help of automatic test pattern generators. Synthesis. Another design task to be performed is the synthesis. In synthesis process, the hardware description is converted into lower level description. For example, a logic or Boolean expression. Logic synthesis is mainly focused on generation and optimization of a circuit at logic gate level. Many available synthesis tools perform synthesis of two level or multi-level combinational circuit and sequential circuit. At this level, the original description can either be in a behavioral view or a structural view, but the resulting description is a structural view, that is a netlist in the lower abstraction level. Synthesis is normally divided into many smaller steps, each performing specific transformations. Some of the main steps are higher level synthesis, register transfer level synthesis, gate level synthesis and technology mapping. Physical design. Logic gates are constructed using transistors. Designing at transistor level demands a different level of dependence on the requirements. Transistors can be modeled at the switch level as a bidirectional switches. At the timing level, among signals are considered with piecewise linear function. At circuit level, transistors are modeled using nonlinear differential equation for currents and voltages. The physical design of transistors can be realized using two-dimensional physical medium with parasitic capacitances and resistances depending on the shapes of the pattern in the different layers. In addition, one needs to deal with layout of subblocks. From an abstract point of view, subblocks are rectangles or polygons with terminals at their periphery to which wires are connected. Placement of polygons and providing interconnection routes are to be handled by placement and routing tools. These layout designs have some timing constraints. The grouping of subblocks in a structural description and the interconnections need to be addressed separately while handling the partitioning of the layout. Simultaneous development of structure and layout is known as floor planning. Verification. Verification is the process of checking whether or not a design meets the specifications and performance parameters. There are three main ways to check the correctness of the IC without fabricating it. These includes prototyping, simulation and formal verification. One can physically build the circuit using discrete components rather than ICs. This common practice is known as breadboarding. It is also possible to use programmable logic devices like FPGA for prototyping. The advantage of prototyping is that it provides real-time behavior of the design. Simulation utilizes computer models to verify the behavior of the circuit. The disadvantages of the simulation tools is that exhaustive test of a large circuit with many inputs and outputs is really impossible. In formal verification, mathematical methods are used to prove that the circuit is correct. The problem with the technique is that executing the proofs by hand is too time consuming. Testing is the process of checking whether the device is properly fabricated or not. The course of action also includes detecting the physical defects of a die or a package during manufacturing process. Due to large number of inputs, an algorithm is used to obtain small set of test patterns. Further, many designers prefer to include built-in self-test, that is BIST, which provides the design for test, that is DFT approach. Let us now summarize certain points which we have discussed in this section. The take home points are: the first, integrated circuits are classified into 4 categories: SSI, LSI, MSI and VLSI. Invention of transistor is the driving force behind designing the VLSI circuits, and the growth in the VLSI technology has helped the user to make their product or gadget more compact and low cost. In the design process, there are 6 steps. The design and development process undergoes through a complete cycle, starting with the simple design, then naturally simulation, synthesis. Once that is over, then next step is let us design the prototype. The prototype can be tested and verified, that completes the chip design process. While designing this IC through these 6 different steps, usually Gazetski chart or Y chart helps the designer to simplify their design. Designing can be carried out at 3 different levels. These could be the abstract domains in which the designer can work. Maybe it could be a physical domain, it could be a behavioral domain or a structural domain. And depending upon the domain that is selected, the design complexity could vary. In addition to that, there are 5 different abstraction levels at which user can implement different ICs. Thank you.